In this video, we will discuss time-independent perturbation theory. We need perturbation theories because most of the time we cannot solve an actual Hamiltonian exactly. But what we can do that for part of the Hamiltonian, we can solve the system exactly. Usually a simpler or more symmetric part of the Hamiltonian that we can solve exactly. So using perturbation theory, what we can do that we can use the solution of the simpler part of the Hamiltonian to build solutions for the complete Hamiltonian. At least we can get corrections on top of the simpler Hamiltonian that give us results that are nearer to the solutions for the actual Hamiltonian. So perturbation theories are actually very important in applied quantum mechanics because that's what we do all the time, that we construct solutions and we find energies of systems which are complicated to solve exactly, but we can construct those approximate solutions using exact solutions of an underlying simpler problem. So in this video, what I'm going to do is going to present the formalism or the derivations, so to say, of time-independent perturbation theory. I will discuss two cases: the non-degenerate case, where all the eigenfunctions have different energies of the underlying simpler Hamiltonian, and the degenerate case, which is also not uncommon. Actually, it's much more common in practical problem than the non-degenerate case. So I will derive the expressions for energy corrections both for the degenerate and for the non-degenerate case. So let's begin with the non-degenerate case, which is simpler to handle. So before I come to this non-degenerate case, let me discuss what the actual problem is in the perturbation theory. So what we want to do that, suppose we have a Hamiltonian which we can write as sum of two terms. So we cannot solve the system exactly potentially for this Hamiltonian most of the time. However, if we break our Hamiltonian into two parts, where this is a part for which we can solve the system exactly, and then we can find the exact energies and eigenfunctions for this Hamiltonian. Let's say if we have a system and we solve it, so let me use the symbol phi for this. So let me call these solutions phi and 0 of this H naught Hamiltonian with energy spectrum E and 0. So the idea is this, that we break our Hamiltonian into two parts such that for one part we know the solutions exactly. So this is these are all the eigenfunctions and these are all the eigenenergies. And the job of a perturbation theory is to find the corrections to these energies and to these eigenstates when we add this term in the Hamiltonian to make this Hamiltonian go closer to the actual Hamiltonian. And that's what we are going to do, that we are going to find corrections to this energy when this term is added to the Hamiltonian. And obviously this spectrum can have two types. One type, for example, in one-dimensional harmonic oscillator, is that for each eigenfunction there is a different value of energy. This is called a non-degenerate case. However, sometimes it happens that we have different states. There are different eigenfunctions, but those different eigenfunctions, some of them can have the same energy. For example, when we solved for these eigenfunctions and eigenenergies of hydrogen atom, we saw that several states with the same value of n can have the same energy. So that's a degenerate case. So we will begin with a simpler case, and then we will go on to discuss the degenerate case. So let me rephrase. So the idea is this, that we have solutions for a simpler Hamiltonian, and we want to find the solution of the complicated Hamiltonian, which has a simpler term plus an additional term. So the goal of the perturbation theory is to find corrections to the energy and the wave function when this term is added. Most of the time our interest is actually only in the corrections of energies, but sometimes we are also interested in seeing how these states are transformed. Okay, so let's come to the non-degenerate case. We assume that for each n, En0 is different. So this is our underlying assumption, and let's assume that for the actual Hamiltonian there are solutions psi n with energies En, and the goal of the perturbation theory is to find better approximation for En and psi n. Okay, to do this, let me break. So let's write our Hamiltonian as H naught plus a term lambda times H1. This lambda helps us build the perturbation theory, because we see that this parameter is important. When lambda approaches 0, our Hamiltonian approaches H naught. When lambda approaches 1, our Hamiltonian approaches the actual Hamiltonian for which we want to find this solution. And since we are going to write these energies and these wave functions as a power series in lambda, this would mean that more terms that we know in the power series of En and epsilon psi n, the better is our knowledge, because more terms mean that we can approximate for a higher and higher value of lambda. And in principle, to find En and psi n exactly, we need to find the infinite number of terms, because only then the series can converge for lambda approaching 1. Okay, so let's begin by expanding our En as a series in lambda with 0th term, with the first order term, with the second order term, and so on. Similarly, we can expand our wave function as 0th order wave function. Ket symbol here, lambda, phi 1, lambda square, phi 2, and so on. So this epsilon En0 and phi n0, they are the solution of this underlying simpler Hamiltonian. And to get better approximation of En and psi n, we need En1, phi n1, En2, phi n2, and so on. Most of the time, these corrections are small as compared to this, which means that with just En1 and phi n1, we have a pretty good approximation for En and psi n, which is called the first order approximation. But sometime, let's say this En is 0, En1 is 0, so to get an approximation beyond 0th order, we have to find this second order approximation as well. Or if you want to make your approximation better from the first order, you can do the second. You can find the second order approximation terms. Okay, so We can find these en1, phi n1, etc. by requiring that en and psi n they satisfy this equation, because this is our basic time independent Schrodinger equation that these en and psi n must satisfy. So let's substitute this en psi n here, and for h let's substitute this part, for en let's substitute this, so we get h naught plus lambda h1. For psi n we had phi n0 plus lambda phi n1 plus lambda squared phi n2, and so on. And on the right side I have en psi n, and en is nothing but en0 lambda en1 lambda squared en2, so on, and phi n psi n is phi n0 lambda phi n1 plus lambda squared phi n2, and so on. So let's multiply these terms on both sides. So here I get phi h naught phi n0 and then with this one I get lambda h1 phi n0. Then this h naught, if I apply here, I get lambda h naught phi n1, and let me take lambda common from both of these terms. There's no other product term here that has lambda in it. We have lambda square and so on. So let's see what are the lambda square term. So if this one multiplies with this one, I get lambda square term h1 phi n1 and if this h naught applies to this term, I get again lambda square term, so h naught phi n2. Any other lambda square term? The next term is lambda cube, so no, we have only these two terms, and then so on. On the right side, I have en0 phi n0, which is independent of lambda, plus this lambda en1 into phi n0. We take lambda common because there are going to be other terms, en1 phi n0 plus this multiplies with this. I have lambda which is common outside, en0 phi n1. Then any other lambda term? No, okay. Plus let's see if there is lambda, what are the lambda square terms. So this multiplies with this, it is en1 phi n1. Then this one multiplies with this, I have en2 phi n0, and similarly this one multiplies with this one, en0 phi n2, and then lambda cube term, then so on. So now we have this equation, and this lambda is an arbitrary parameter, and if we want both sides to be equal for all values of lambda, we need to make sure that the coefficients of all powers of lambda are the same on both sides, which means that if I compare this with this, actually get this equation, which is already here, h naught phi n 0, e n 0 phi n 0. So this we know already is equal. So from here, you see that this has to be equal to this. So h1 phi n 0 plus h naught phi n1 must be equal to en1 phi n0 plus en0 phi n1. This is one equation, and the other equation we can get by comparing this lambda square terms. If I compare them, I get h1 phi n1 plus h naught phi n2. This must be equal to this term en1 phi n1 plus en2 phi n0 plus en0 phi n2. So these are the two equations, and with this one we need to solve these equations to find, and then of course there are more equations. You can compare the lambda cube term from here, lambda cube term from here, and you will have yet another equation, and so on. You need more and more equation if you need higher and higher order corrections to the energy. To find, let's say, first order and second order corrections, these are all the equations that we need, because they have en0, they have en1, they have en2, similarly phi n0, phi n1, and phi n2. Okay, so these are the three equations that we will be needing again and again. All right. So to begin, finding the energy corrections, let me first write that. First we are interested in first order corrections. Okay. So for this, let me begin from this equation. This is h1 phi n0, h naught phi n1, en1. Let me actually write it here because we will need it. H naught phi n1, h1 phi n0 is equal to en 0 phi n1 plus en1 phi n0. So let's take its inner product with phi n0 from left. So if I operate it here, I get h naught phi n1. Let me just say that this is the equation that came from the earlier board. So this one, if I apply phi n0 here, if I apply phi n0 here, this is just a scalar, this gets out. Phi n0, phi n1 plus en1, phi n0, phi n0. So here, first of all, I see that this h naught, when applied to phi n0, will give us simply en0. This is a Hermitian operator, gives the same eigenvalue either it applies here or here. So when it comes here, En0, and then I have this phi n0, phi n1 term. This is as it is, phi n0, phi n0. This is En0, phi n0, phi n1 plus En1. This is phi n0 inner product with phi n0, which is 1 because there are the normal functions, and we also see that this cancels with this, which means that first order energy corrections are very easy to find in the non-degenerate case. If you have a non-degenerate set phi n zeros and you want to find first order energy corrections because of the additional Hamiltonian term h1, all you need to do is just find this inner product for each n, and you will keep getting the first order energy corrections. What about the correction to the eigenfunction? So this phi n0 is the eigenfunction of h0. What's the first order correction to this eigenfunction when we have this h1 term? So to find that, let's operate on this equation from left with some phi k 0, where this time I'm taking that k is not equal to n, because when k was equal to n, I already operated this equation with phi n0 and got this equation, and we reached here. Let's now see what we get if we operate it with a general phi k0, where k is not now equal to n. So I get phi k0 h naught phi n1 plus phi k0 h1 phi n0 e n0 phi k0 phi n1 plus e n1 phi k0 phi n0, and just to remind us that this is for k is not equal to n. If k is not equal to n, we can quickly see that this is 0, because phi k phi n, when k and n are not the same, they are orthogonal, so this inner product is 0. And from here I can see quickly that this h naught, when operates on phi k, I get ek of 0 phi k phi n1, and here I get phi k0 h1 phi n0 en0 phi k0 phi n0. We can take this to the other side, and there is phi k0 phi n1 common, so which means that this phi k0 h1 phi n0, this thing is common in this and that term, so I take it to the other side and take this common, so I will be left with en minus ek. So let's bring that en minus ek on this side, and we have this is 1, this is 1, this is 1, this is 1, like this. So this is important, because what this gives us the projection of this phi n1 onto each of phi k0 in terms of phi n and phi k0s, en0, ek0s, and h1. Because we need this projection, because to write any state we can use these phi k zeros as bases, because this is an orthonormal set of a Hermitian operator. So we can represent any other state as a superposition of these phi k zero states, and using that we can, let's say, write this correction phi n 1 as just a superposition of these state. So phi k0, phi k0, phi n 1. So I can express this phi n1 as in this phi k0 basis like this. So this phi n1 onto phi k0, this is the projection of phi n1 on each of the basis vector, and then this is simply the basis vector indicating that for this projection, this is like sort of a unit vector, and we keep on adding all the components to get this phi n1. So we have this representation, and if I take, this is the sum from k is equal to 1, 2, 3, 4, 5 up to all the values, maybe infinity if this is an infinite set. But if I separate the k is equal to n term out, so let me take k is equal to n term out of this sum phi n 0 plus. Now in my sum k is not equal to n, but I still have phi k0, phi k0, phi n1. Now let's see what this phi n0, phi n1 is. To do that, we can come back to this expansion of this psi n that we have, and demand that for this psi n state is normalized, which is the perturbed state for the this Hamiltonian H. And since we are working only for the first order, we can say that this psi n state, if we are taking it the first order in lambda, should be normalized, so which means that it should be 1, 1 should be equal to, if I flip it, I get, let's say, lambda square phi n2 plus lambda phi n1 plus phi n0 into phi n0 plus lambda phi n1 and so on. So this first term is phi n0, phi n0. And this is without lambda, and then we have this lambda phi n1, phi n0, phi n1, phi n0, and then if I inner product this one with this, I get lambda phi n0, phi n1, and then there are other terms. This is 1 because phi and 0 are already normalized. So if this is 1 and there is 1 on this side, and we want this to be normalized, so up to first power of lambda, if it is only up to first power of lambda, this part should be 0, this part should be equal to 1, so this 1 is 1, so this part should be 0, which means that phi and 1, phi and 0 should be equal to the negative of phi n 0, phi n 1. And since this is the complex conjugate of this number, because this is phi n 1, phi n 0, this is phi n 0, phi n 1, and we know that the complex conjugate of a number is equal to negative of that number only if that number is purely imaginary. So it means that phi n, this term that we were looking for, we now know that there has to be one thing true about this, that this is some iota times a real number. Which means that phi n 0, this phi n 1, I can write it something like iota a phi n 0 plus a part which is perpendicular to phi n 0. There's a part in this phi n 1 which is proportional to phi n 0, and the proportionality constant is iota a, because if I now take its inner product with phi n 0, this will go away because this is a part which is perpendicular to phi n 0. So the dot product of this part with phi n 0 is 0, and dot product of this part with phi n 0 is iota a, so this is iota a. So we see that phi n 1 can be written as a part parallel to phi n 0 and a part parallel to and a part perpendicular to phi n 0. So with this thing, let me now see if I use phi n 1 in our, so in this side up to in this side up to lambda, I get phi n 0 plus lambda, and in place of this phi n 1 I have iota a part parallel to phi n, and then lambda into a part perpendicular to lambda. I'm not writing the lambda square in higher order term because we are approximating it up to lambda. So this is now equal to, so this is 1 plus iota a lambda, and let me write it 1 plus iota a lambda phi n 0 plus lambda part perpendicular, and up to lambda this is nothing but iota a lambda, and I can take this term common from everything after this, phi n 0, and actually let me write it something, okay. Let's write it like this, perpendicular part and some terms of the order of lambda square. Now you see, our wave function is something like a global phase into this. I can take this thing common from everything else as well. However, each normalized function can have a global phase anyway, because when we normalize a function, we find the value of constant only up to the magnitude of that constant, and we can select a phase whatever we want. So for this one, let's choose ourselves that a is equal to 0. So let me just say we can choose any other value of a and the perturbation theory will still work out as it is, but it's convenient to choose this a is equal to 0, because what this will do is that once a is 0, over here it will mean that we are choosing our phi n 1 to be perpendicular to phi n 0 only, which means that we are choosing for this dot product to be 0, and once this dot product is 0, this term is 0, so essentially our phi n 1 is perpendicular to phi n 0, and it only have this expansion. So let me write it. this means that our phi and one correction term is the sum over all k's except for term k is equal to n is phi k0, phi k0, phi and 1. However, we have already computed this term. If you see right here, so let me put the expression for this from here, and I get sum over all k's except when k is equal to n. I get phi k0, phi k0, h1, phi n1, en0 minus ek0. So this is the correction to the wave function. Let me see if my expression match my notes. Good. And let me just remind you that this means that our straight psi is the sum of this one and phi n0. Okay, so we have the first order perturbation corrections complete. Let me just discuss what does this mean graphically. So we had this unperturbed wave function phi n0, and for the first order perturbation we chose our phi n1s such that they are perpendicular to this original function. So it means the total wave function psi is something like this up to first order in lambda. So we only have one term, so the psi n is slightly away from the original phi n's of the h0 function, and this is nothing but the sum of phi n0 and phi n1. Okay, so this is how we were able to get the first order corrections to energy and wave function. Let's now see the second order correction. And since we are mostly interested in corrections to energy, I'm only going to work out the corrections to energy. And for that, we are going to be taking this equation that we have here and simply operate it with phi n0 from the left side. So if I do that, I operated this equation with phi n0, I get phi n0 h1 phi n1 plus phi n0 h0 phi n2, this en gets out, phi n0 phi n1 plus en2. When phi n0 comes here, this will be 1, so I'm not writing it. And I will have an additional term en0 phi n0 phi n2. Okay, so if I look at this term, this h0 will operate on phi n0 and I'll get en0 into phi n0 phi n2. This is exactly the same term as this one, en0 phi n0 phi n2. So this cancels with this one, and we have from here, let me write, So this H1, I don't know how it operates, so I'm going to write it phi n0, H1, phi n1. This is equal to this thing. So this is phi n0, phi n1. So this becomes E n1, phi n0, phi n1 plus En, this En0. Sorry, not En0, because this is already cancelled, this is left, En2. Okay. So this is what we have, and from this I can easily see that this is 0, right? Because we have chosen our phi n1 to be perpendicular to phi n0, so that term goes away. So En2 is just equal to this term, and this phi n0 h1 phi n1 we have already worked out. That over here I'm looking for phi n1 h phi n0. So phi n1. So this phi n1 we have already found right here. This is our correction function for first order corrections. So let me substitute this phi n1 from here in here, and I get sum over k when we have to exclude k is equal to n. So phi n0 operates here. This phi n0 h1. This operates on this phi k0. Phi k0, and this term is there, phi k0 h1 phi n0 over En minus Ek, or this means that En2 is, so this is conjugate of this, so I get sum over all terms except k is equal to n, phi n0 h1 phi k0 mod square En0 Ek0. So these are our corrections, second order corrections to the energy. And of course, we are working with non-degenerate case that all energies for different n are different. So this is never going to be equal to 0 because they are all different. So all we have to do is just evaluate this sum. So let me write it explicitly. For example, you are looking for sum En2, and for that you work out this for phi 10, take its square, divide it with En0 minus E1 plus phi n0 h1 log phi 2 mod square En0 minus E20 and so on. Except that you have to exclude the term where whatever n you have chosen for these two indices are not the same. So you sum over all of these terms to get the correction, second order correction to the energy. And if this is an infinite series, because sometimes this number of functions, 5k's, they could be infinite. Then usually after a while the terms keep on decaying. The terms, the magnitude keeps on decaying, so that only after a few terms, when the overlap of this phi n with these phi k's begin to decrease, you can stop this sum. Otherwise, if these terms don't go to zero, you will have to evaluate all of the terms. Okay, so this is the derivation for non-degenerate theory, and we can see that this theory cannot work when we have a degenerate case, because in degenerate case, for some of the eigenfunctions of H naught part of the Hamiltonian, energies are the same, which means that there will be a zero here and we will be in trouble. So let's now derive the expressions for the degenerate perturbation theory, and for that I need to shift to another set of board. So let's go there. Okay, so the degenerate perturbation theory assumes that some of distinct functions phi n have the same energy En. And let's say, so out of these functions, so for example, let me write it like this. So we have phi 1, phi 2, phi 3, phi 4, and so on. Suppose it's something like this. Suppose that this has some energy, let me call it like 2 electron volt, this has energy, I don't know, 3 electron volt, and this has energy 4 electron volt, this has eigenenergy 4 electron volt. Let's say phi 5 has 4 electron volt, then phi 6 has again 5 electron volt, and so on. So for these states which have different energy than everything else, you can still use the non-degenerate perturbation theory. For example, correction to phi 1 can be found from the non-degenerate perturbation theory that we just studied. Correction to phi 2, we can still use non-degenerate perturbation theory because its energy is different than everything else, and there won't be any place where En, Ek will be 0. However, once you have found these, similarly you can find correction to phi 6 because its energy is different from other energies. However, for these states, we need to use another method to find corrections to these energies. For example, all of them have the same energy, but we could get 3 other states under the perturbation Hamiltonian that could have different energies, or some of them could still have same energies, but some of them could have different energies, and their wave function would also be a mixture of these wave functions or eigenfunctions. So now I'm going to concentrate on this part of the eigenfunction spectrum where the eigenvalues are the same. And suppose that we have we relabel these functions like this. Now I'm going to put an extra label I, that all of these have the same eigenenergy En, even though they're all different eigenfunctions. For example, this one, and this one. So I have introduced another index I, and suppose that we have capital N number of degenerate states in this one. So it means that I can now resuppose my trial wave function psi n, which of course would be something like this, that let's say it's a superposition of all of these degenerate wave functions. So there's this term proportional to this, and then there is a first order correction, and then there's a second order correction, 2, and so on. So this is how we are going to suppose our eigenfunction. The energies are still going to be assumed the same, that the energy En corresponding to this perturbed state is something like En0 plus lambda En1 and so on. And this En0 corresponds to each of this phi ni, and this En1 is the first order correction to this energy, and so on. Okay, so now actually our job is twofold. I'm going to find the first order correction to the energy, but also I'm going to find these coefficient Ci's to determine this superposition state for that energy. Okay, to do this, let's recall that whatever our solution psi n is and En is, they have to satisfy this eigenvalue equation. So let me substitute for h naught plus lambda h1, and for psi n we have sum over I Ci phi n 0 I plus lambda phi n1 and so on. En is En0 lambda En1 and so on. Similarly, psi n again is sum over I Ci phi ni 0 plus lambda phi n1 and so on. So this time I'm only interested in the first order correction, so I'm not even going to bother about lambda square and so on terms. So we see immediately that the terms independent of lambda are this h naught, this sum over I Ci phi ni 0, this En0 into this, sum over I Ci phi ni. There's nothing surprising here, because all of these eigenfunctions are the eigenfunctions of h naught with the same energy En0. So we get this equation. Now for terms proportional to lambda, I get h naught into this, h naught phi n1, and I get this into this plus h1 sum over I Ci phi n0, and on the right side term proportional to lambda are this En1 sum over I Ci phi n I, and then this En0 into this phi n plus En0 phi n. Similarly, to find this En1, we can take its inner product with phi n0 from the left. So phi n 0. When this phi n 0 operates on this, so that's this one, phi n 1 plus h1 plus sum over I ci phi n 0 h1 phi ni 0. And actually now instead of taking dot product with phi n 0, we should have taken with something like phi n j, because we have these new label phi n I to our eigenfunctions. So for to make it different from this, let me take phi n j. So here is phi n j. Similarly here I will have en 1 sum over ci phi n j 0 phi n I 0, and here I get en 0 phi n j 0 phi n 1. Now when this h naught operates on this phi n j 0, we get en 0. So en, this term then becomes exactly the same as this one. This has en 0 phi n j phi n 1. This will also have phi n j phi n 1. So this goes away, and what I'm left with is this term, sum over I 1 to n ci. And let me give a special name to this product. Let's say it's h1 ji, and on the right side I have en1 ci. Now this product phi n j into phi n I, this will be non-zero only when j is equal to I, and it will be 0 if j is different than I, because these eigenfunctions which have the same eigenvalue en 0, but they are still orthogonal. So it means that when they are different, the inner product will be 0, but only when they are same, when j is equal to I, this product will be 1. So let's simply put C is equal to j, where this new symbol that I have introduced, h1 ji, is nothing but a shorthand for phi n j0 h1 phi n 0. And we now have a system of equation that we can solve to find en1 and to find all the coefficients. Let's see how. To see how we can solve for these coefficients, let me write this equation explicitly. This is C1 H1 J1 plus C2 H1 J2 plus C3 H1 J3, so on all the way up to Cn H1 Jn is equal to En1 Cj, where j varies from 1 to n, because j could be anything. J could be 1, j could be 2, j could be 3. So this is our general equation where this h1 etc. they are formed from here. Now if I write this equation for each j, keep it here. So for j is equal to 1, I will get C1, H1, 1, 1, C2, H1, 1, 2, so on, Cn, H1, 1n, En, 1, C1. Similarly, C1, for j is equal to 2, I have 2, 1, C2, H1, 2, 2, Cn, H1, 2n, En1, C2. And we have j equations, the last would be C1, H1, N1 plus C2, H1, N2, Cn, H1, and then En, Cn. And if I express this matrix this in a matrix equation, I get this. So there is this H1, 1, 1, H1, 1, 2, H1, 1n, H1, 2, 1, H1, 2, 2, H2n, and you get an idea. Here I have C1, C2, C1. This En1 is same everywhere, so it's common. This is an eigenvalue equation, essentially. So I can rearrange it like this. So you can bring. So let's actually write it like this. So let me call it some H1 matrix. This is C column vector, En1, C. I can bring this thing here and take C common, H1 minus identity En1 dot C is equal to 0. Now we can see clearly from here, from let's say, might have seen this thing in linear algebra, that if you have an equation like this, Ax is equal to 0, if this A is non-singular, it means its inverse exists. So if its inverse exists, this means that I can multiply with A inverse from both sides, and this is identity, which means that X is equal to 0. So if A's inverse exists, then the only solution of this equation is X is equal to 0. However, so then if A is non-singular, X is 0, which means that for our case, if this is our A, if this is non-singular, all C's are 0, which means the state size is equal to 0, which means no combination or no perturbation on the original system, which is not an interesting case. So to get a non-zero C, we have to make sure that this is not singular. So if A is not singular, we can have non-zero solution for X. So this means that to get non-zero solution for C, we have to make sure that the determinant of this matrix is 0. And from this equation, you can solve this equation and find En1. So this is how, because everything in H1 is known. H1 is nothing but these terms, that since these phi ni and phi nj are all known, because they are the eigenfunction of H0, and we have to apply this H1 on these to find these terms. And once we have these terms, this is simply identity. So we can solve this determinant to get En1. And once we have these energies, we take these energies and put here one by one. So let's say if this is an n by n system, we can get up to n values. So we put first value here, then we solve this equation and find C1, C2, C3 all the way up to Cn, and that's our first perturbed state with the correction to energy that one. So then we put the second value here and solve the system again, find new C's, and that's our second perturbed state, and so on. I'll do a couple of examples in the next lecture, and you'll be able to see how we can use this theory to find these corrections to the eigenvalues. Okay, so with this, we can say that we now have a method for computation of corrections to the energies. At least we have a complete system for first order energy corrections. If it is non-degenerate, it's simply this. So let me write it simply. For En1, it was phi n0, h1, phi n0. So for non-degenerate case, it's pretty quick and easy. All we need to do is just find these corrections right away. But for the degenerate case, we need to find these terms for all the degenerate eigenfunctions, which we are calling h11, h12, etc. And once we have that, we set up this matrix equation. We put its determinant equal to 0, solve for En1, and for each value of En, we put them here and we find these coefficients to get our psi, because our psi, if you recall, was the first term in the psi was Ci sum over I Ci phi n I C. So whereas here the first order correction to the functions were also a series, which is given in the other report. Okay, so thank you.